In part A, the question says draw a voltmeter symbol on the circuit diagram of figure 1.1 to show the voltmeter reading the potential difference across the heater. So there are two ways of doing it. One is that the voltmeter could be connected across the power supply. So whatever the EMF or the voltage of power supply is, the same is going to appear across the heater. Or we could directly connect the voltmeter across the heater over here in parallel. We know that voltmeter is always connected in parallel. So I'm making a voltmeter over here, and this would be connected in parallel with the heater. So the two wires going to heater, they would be connected across the voltmeter, and this is the parallel connection of voltmeter, which would give us the voltage reading or the potential difference reading of the heater. The next part says the specific heat capacity of water is 4.2 joules per gram per degree centigrade. Examine the apparatus setup shown in 1.1. Suggest one practical reason why your calculated value of C is inaccurate. So if we examine the apparatus given, we can see that there would be heat loss to the surroundings from the sides of the beaker and from the top of the beaker too. So this could be one reason. The other reason we can see is that the heater is too close or it is touching base of the beaker, which would also cause some heat loss to the surrounding or to the beaker, and that heat would not be uh, given to the water directly. Welcome to this tutorial. I'm solving question number 1 of paper 4-2 May June exam series of 2019 of O-level GCSE Physics 5054. The question says a student determines an approximate value for the specific heat capacity of water by an electrical method. So the objective is that during this investigation, the specific heat capacity of water is to be determined, and we are using an electrical method to transfer heat to the water. The specific heat of a substance is the amount of thermal energy needed to raise the temperature of 1 gram of the substance by 1 degree centigrade. So the definition of specific heat capacity of any substance is written here. He sets up the apparatus as shown in the figure 1.1. So in this apparatus, we can see that a power supply is being used. There is a switch present over here which connects and disconnects the power supply and the current in the circuit. There is an ammeter here to measure the flow of current, and then we have a heater in the water, and then we have a thermometer over here to measure the temperature of the water in this beaker. He pours a mass m of water into the beaker where m is equal to 100 grams. So 100 grams of water is added into the beaker for this investigation. He places a heater into the water in the beaker. So there is a heater over here. He connects a voltmeter to measure the potential difference across the heater. So the potential difference across the heater is to be measured. Since this is the only component connected in the circuit, so whatever the potential difference or the EMF provided by the power supply would be, the same potential difference is going to appear across the heater. In part A, the question says draw a voltmeter symbol on the circuit diagram of figure 1.1 to show the voltmeter reading the potential difference across the heater. So the voltmeter should be connected in a way that its reading should give us the potential difference across the heater. So there are two ways of doing it. One is that the voltmeter could be connected across the power supply. So whatever the EMF or the voltage of power supply is, the same is going to appear across the heater. Or we could directly connect the voltmeter across the heater over here in parallel. We know that voltmeter is always connected in parallel. So I'm making a voltmeter over here, and this would be connected in parallel with the heater. So the two wires going to heater, they would be connected across the voltmeter, and this is the parallel connection of voltmeter, which would give us the voltage reading or the potential difference reading of the heater. In the next part, the question says the student measures the initial temperature of the water and records it at time t is equal to 0 in table 1.1. So we have initial temperature of the water as 21.5 degrees centigrade. He closes the switch, starts a stopwatch, and records the temperature theta of the water every 60 seconds for 6 minutes. So as we can see in the table, the temperature starts rising. He records the current I in the heater and the potential difference V across the heater. His measurements are 4.0 amperes, the value of current, and 14.8 volts, the reading of the voltmeter. He opens the switch, so now no current is flowing through the circuit. The heater would stop heating. The reading of the thermometer at t is equal to 240 seconds is shown in this figure. So this is the part of the thermometer which is showing the reading at 240 seconds. Read the thermometer and record the temperature in table 1.1. So we can see that from 35 to 40 we have 5 divisions. So it means that every small division is representing 1 degree centigrade. This first line after 40 would be representing 41, and this would be representing 42. And the level of liquid we see here is in the mid of 41 and 42. So the reading that it is giving to us is 41.5 degree centigrade over here. So this reading would be recorded in the table. So I'm writing 41.5 degree centigrade. Now the next part says state why it is important to, number one, ensure that heating coil is completely immersed in the water. So when the heating coil is not completely immersed in the water, there would be heat loss to the surroundings. And when it is completely immersed in the water, all the heat would be transferred to water only. So I'm writing so that all the heat is transferred to the water. That is why it is completely immersed in the water and no portion of it is left out of water. Number two, stir the water before recording each temperature. So stirring is important here because it ensures that the heat energy is uniformly distributed within the water. The region surrounding the thermometer should have the same amount of energy as the remaining portion of the water. If that portion has lesser energy, then the temperature shown would be lesser than the actual one, or if the portion surrounding the thermometer has larger amount of energy as compared to the other areas or regions of water, then that is going to give us a larger reading than the actual one. So we would stir to ensure that all the water is at the same temperature. The next part says on the grid in figure 1.3 plot the graph of theta temperature in degree centigrade on the y-axis against T in seconds on the x-axis. So this is the first information. And secondly, start the temperature axis at 20 degrees centigrade. So on the y-axis, when we are writing the values according to the scale that we are going to use, the first value written should be 20 degrees centigrade. Draw the smooth curve of best fit. Then after plotting the points from the table, we are going to draw the smooth curve of the best fit. Okay, so the first thing in the questions of the graph is to label the axis. So I'm writing theta means temperature in degree centigrade on the y-axis and time in seconds on the x-axis. The second thing we have to do is to decide what type of scale are we going to use. So if we observe the values of y-axis, we have minimum value of 21.5 and the maximum value of 48.5, and we have total of 1 2 3 4 5 6 and 7 large boxes. So we could use a scale of, on the y-axis, two big boxes or the square represent 10 degree centigrade, and similarly on the x-axis the value of time is starting from 0 and going all the way to 360, and on the x-axis we have 1 2 3 4 5 6 7 and 8 boxes. So we could use the scale as one big box. It represents 60 seconds on the x-axis. So according to the scales used, I am going to mark the values now. So for the y-axis, the starting value would be 20 because we have to start the temperature scale by 40. Then we have 30 after two boxes or big squares. Then we have 40 over here, and this value would be 50. So all the main values are marked on the y-axis, and now we start the values on the x-axis. So we start with the value of 0 over here, then we have 60, 120, 180, 240, 300, 360 and 420. We could also mark here 480 value. So the second thing, making a linear scale according to the given instruction, is done. First we marked the axis, the y-axis and the x-axis. Then we decided according to the given values what scale should we use, and thirdly we marked the values or the numbers on the x-axis and the y-axis. The third thing that we are going to do now is to plot these values. So we have 0, 21.5. This is the first point. 21.5 would be marked over here. Next point we have from the table is 60, 27.0. So on the time of 60 we have 27 temperature, a temperature of 27. So 25, 26, 27. So this point would be marked over here. The third point we have is 120, 32. So on the time of 120, I'm going to mark a point of 32 over here. This would be the point. And the next point we have is 180, 37. So 37 would be marked here. On the time of 180. Then at 240 we have the value of 41.5. So 41.5 would be marked over here at 240. At 300 we have the value of 45.5. So that would be marked over here. And lastly we have the value of 48.5. So 48.5 would be marked here. So I've plotted all the points, and now I'm going to make small circles around the points. Now, the third thing is done. First, we name the axis. Secondly, we decided the scale that we are going to use. And the last thing that we are going to do here is to make a smooth curve of best fit. So this could be a smooth curve of best fit according to the data given to us. Now, the next part says use your graph to calculate the temperature rise or the change in temperature delta theta of the water in the first 200 seconds of heating. So at 0 degree centigrade we have the temperature of 21.5. I'm going to note it down here, and from the graph we have to calculate the value of temperature at 200 seconds. Now in this graph we can see that each small box is representing 6 seconds. So this is 186 seconds, 192 seconds, 198 seconds. So the time of 200 seconds would be a little after or 1/3 distance after the third small box. So I'm making a line from here and I'm taking it all the way to the curve. So it matches the curve at this point, and now I'm going to connect it on the y-axis. So the value that we are getting, it is a little lesser than 39. So I could take it as 38.9. So this is the value that we are getting at 200 seconds, which is 38.9. So if now we try to find out the difference in the temperature, that would be represented by delta theta, and for that I'm going to subtract 21.5 from 38.9. So it comes out to be equal to 17.4 degrees centigrade. So the temperature difference according to the graph that I have drawn is 17.4 degree centigrade. Now the next part says calculate the thermal energy supplied to the heater in the first 200 seconds and give the unit. Use the equation below. So we have the equation where we have to plug in the value of voltage, then the value of current, and then the time would be taken as 200 seconds. So I'm using these values 14.8 and 4.0 amperes. So the answer we get is 11840, and if I convert it into standard form, then it could be written in 3 significant figures as 1.18 and in 2 significant figures 1.2 10 raised to 4 joules. So the final answer in 2 significant figure, if it is written, it would be 1.2 into 10 raised to 4 joules. Calculate a value for the specific heat capacity C of water. Use the mass given at the start of this question, which was 100 grams, your answer to C part 2 and D part 1, and this equation. So the value of mass was 100 grams, the value of C we have to calculate, and the temperature change was coming out to be 17.4. The value of energy that we got was 1.2 into 10 raised to 4 joules. So the value of C would be 1.2 into 10 raised to 4 divided by 100 into 17.4. So it is 6.896, which would be rounded off to 6.90 joules per gram per degree centigrade. So the answer is 6.90 joules per gram per degree centigrade. The next part says the specific heat capacity of water is 4.2 joules per gram per degree centigrade. Examine the apparatus setup shown in 1.1. Suggest one practical reason why your calculated value of C is inaccurate. So if we examine the apparatus given, we can see that there would be heat loss to the surroundings from the sides of the beaker and from the top of the beaker too. So this could be one reason. The other reason we can see is that the heater is too close or it is touching base of the beaker, which would also cause some heat loss to the surrounding or to the beaker, and that heat would not be uh, given to the water directly. So I'm writing thermometer is too close to the beaker. And the next part says state one improvement to the apparatus that produces a more accurate result. So that, if related to thermometer, could be place the thermometer correctly and not touch it with the beaker. So it should not be too close to the beaker. That would improve the results. Another student repeats the experiment and forgets to switch off the heater. At the end of the experiment, the temperature of the water continues to rise until it reaches 82 degrees centigrade and then remains constant at this value. So the temperature is not rising further. Suggest one reason why the temperature of the water stops increasing when it reaches 82 degree centigrade. So according to our normal observation, the temperature of a substance stops increasing when the state of the substance is changing. This is what normally happens. But in case of water, this is not the case here, because the boiling temperature of the water is around 100 degrees centigrade. So the temperature of the sample is clearly lesser than that point. The other reason could be the heat gained by the water is equal to the heat lost by the water, and that is why there is no difference in the temperature being seen. So this would be the correct answer here. So I'm writing heat loss is equal to the heat gain for the water at this temperature, because when the temperature of a substance increases and there is a larger difference of the temperature of the substance and the surrounding of the substance, then the heat loss process fastens, or it becomes a very rapid process. So when the temperature reached 82 degrees centigrade, the water started to lose its heat quickly and the temperature wasn't increasing further. So the question ends here with this part.